All right, you're going to draw this in the air for me, and I'm going to draw them on the board. I really want to make sure you're ready for your test on Monday because it's cumulative and it's a lot. So, phase diagram, what's it look like, Cody? Just give me how many lines are on it. This was, I wasn't too specific. Give me more. So here's our axes, right? Like a Y, thank you. So it's just basically 2 lines. So you've got this and this. What's this section called, everybody? Solid, this section, and what's this axis? Pressure, and so it's literally telling you the state of matter at every temperature and pressure known to man. You also can determine melting points and freezing points and triple points and sublimation points and etc. from this data. And what's normal again for us? Normal pressure, 1 atm. So we could say 1 atm, and you could determine the point at which the solid phase went to liquid, or the liquid went to gas, and so forth. What does a heat curve look like, Liam? Heat curve. Like a little staircase, right? Okay. So we have a staircase. What's this right here, everybody? Solid. This. So the phase change of fusion or melting. I'm just going to put delta H fusion there, that we remember that kind of is synonymous. This section, liquid. This is delta H vap, right? Vaporization, and then this section, gas. Okay. Axes here. Temperature, good, and either time or kinetic energy or heat added, good. And that's because we really need to be sure that we understand that temperature is always going to be generally measured in what? Celsius, because we literally have measuring devices that measure in Celsius. If we're talking about gases, though, temperature must be recorded in what? Kelvin. And heat is totally different, right? Temperature and heat are 2 different things. Heat will be recorded in what unit? Joules. Good. J for joules. Okay. Cool curve, everybody. What's reverse? Flip that, and then we're done. Okay. So you start off high, like this, and you pull down. But this very much reflects what's here. Reaction coordinate, also known as a reaction diagram, also known as a potential energy diagram. Alyssa, what do you think? Can you give me one of those? And just draw it in there for me.
I know where it goes up.
Well, it goes up. I was good with that. And then you said down. I was like, okay. So it goes up, and it kind of hangs high. And then the other one is going to go what? Up, and then... No, it always has to go up first. Always. It starts higher. I started mine way too low because I couldn't get past that. So it goes up, and it falls way down. Okay, so this was in which kind? Endo or exo? Endo. And this one is exo. What is the axis on the y-axis here? What kind of energy? It's also known as a potential energy diagram. So if you ever asked about a potential energy diagram, it's the same thing. So this is potential energy, and this is usually like reaction progress or time or something like that. Okay? What's significant that we should know or be able to determine from these? Yeah, CJ? Okay, so we should know reactants are here, products are here, and we have not gone in depth about that, but I did tell you guys activation energy was where the peak was. Good. But there's something more important that's definitely relevant to what we've learned. Where would delta H be? Somebody help me out here. Where would delta H be?
It's from the beginning of the graph.
Right, it's from literally where the reactants are in terms of their potential energy to where the products are in their potential energy. So we just kind of branch those two and say, okay, that's the magnitude difference, and that's called delta H. If it's endo, the delta H is what? What sign? Positive. Good, I heard you. And this one over here is a delta H of negative. Good. What was the other one? Solubility curve. What's it look like, Dean? Solubility curve. What's it look like? shush. Your name's not Dean.
Oh, it's like a bunch of lines.
Oh, good. Bunch of lines. That's a novel idea. Okay. So like this, and that. What's the dash one? I guess. Good. What are the what's the y-axis? Say again? I heard somebody. Grams of solute per 100 grams of water or solvent. I'm saying water because that's generally our solvent. And what's the bottom axis? Temperature. And what can we tell from a solubility curve? Saturation, which will be where? On the line for every specific content or solute present would be saturated is on the line. And if you put in more than that, where would that point fall in the graph? Above, right, supersaturated. If it were below, it would be unsaturated. I think that's all the diagrams we have right now. We'll have a couple more by the end of the year, but it's starting to get cumulative, so I wanted to show you a couple of this now. Okay, so Socrative, it's a 3-question warm-up assessment of your knowledge so I can see what the heck you don't know before Monday. Also known as just a quiz, because what else do you want to call it? I don't know. Then it's coming up with a different term that's less scary. He will let me know what it is later. You have a calculator, you have a periodic table probably. You don't need any of your notes, you don't need any of your problem sets. It's okay if they're nearby. Like, I don't care if they're nearby, but I want you to see what you can do from your head so you can see what's your success level on this. It will give you instant feedback and a final score so you can see if you need to study. I'm going to say you probably need to study. If you're wrapping up, just finish wrapping up what you gotta do. I want to at least see your results. So, I don't have a length requirement on the homework. You'll notice this is homework for today and tomorrow because I'm not teaching you new information between now and Monday. We're practicing today, and then tomorrow, I got to tell you guys I have to get glucose testing, gestational diabetes. You know, people have to get that done, so I have to be at the doctor, so I won't be here tomorrow. But instead, I need to start a puzzle on your own because you've done that recently. I have you starting your end of year review PowerPoint. So if you are having me on my website, you can actually go ahead and see what's going on. But it's basically a single slide on each concept we've learned with a question peppered in maybe every 5 slides or so. So that's a really good resource to use, especially before our cumulative test on Monday, because one, it reviews some old stuff that maybe relates to what we're learning now and what we learned with gases and thermo, and it has gases, thermo, and solutions review embedded in it. So we're kind of killing 2 birds with 1 step. Starting interview review and reviewing for a test on Monday. So that's what you guys are doing tomorrow in class. But this, I do want your personalized study guide. Like I said, no length requirement, but make it robust enough that it makes sense to you and it works for you, whatever, like I said, personalized. And it's handwritten because your brain remembers twice or 3 times as much more that you write than what you read or type. So eventually our brains will get to the point where they remember things we type better, but there's just no connection between that and the paper. So that's why I do want something handwritten, not like a Google Doc, not like a Quizlet and so forth. Okay? So can we handle that? We're good? Okay, so we're going to go ahead and start our lab information, information regarding our lab. If you've got a buttload of missing work, you're not doing the lab. It's mainly because I'm more concerned about your personal success in this class than you learning how to make ice cream. Okay? So if you've got a bunch of missing work and that you're not going to have time to do that on your own, you need to use this time wisely. So the gift of time is now here for you. If you got a missing assignment like homework or something, get that to me next week. Okay? Otherwise, make your own personal choice. But most of us are doing the lab. To my understanding, most of us are doing the lab. I have a bunch of stuff I'm still grading, so I'm getting there. And that's like half of it. So I will get there. All right, so we're going to watch a quick video on making ice cream. You can even use this as like the purpose statement for your lab. Ready? Purpose statement for your lab. Jaden, what's up? Excuse me? Leave it on your desk? So you guys have PS 15, 16, and 1 through 8 on your desk. PS 15, 16, and 1 through 8 on your desk. That was what the warm-up required you to do.
Welcome to summer. The sun is shining, it's hot out, and you have the beach on your mind. And we know just what you're craving to cool off: ice cream. This delicious treat comes in many different flavors and forms. hard ice cream, soft serve, custards, and sherbets. But have you ever thought about how these varieties are created? Well, we talked with American University's Matt Harding. Turns out the ice crystals in ice cream determine the consistency.
What you're doing when you make creamy ice cream is you control the size of ice crystals in your ice cream. So we're going to start off with this hexagonal shape for a growing ice crystal. As you go along, you add more and more ice to the outside of your growing. Eventually, we get really large ice crystals.
So the bigger the crystal gets, the harder and crunchier your ice cream gets. If you don't want to crunch yourself a treat, you want your ice crystals to be small. But how do you do that? There are two ways. First, put an emulsifier in it. Ice cream is a mixture of water and fat. These two substances naturally want to separate. If they separate, like middle school kids at a dance, the water molecules will hang out by themselves on one side and will be more likely to form large crystals upon freezing because of their interactions. An emulsifier keeps the water molecules and fats together.
Why is water over here and fats over there? Okay, polar and nonpolar, like dissolves like. And then the emulsifier is what's going to help bring them together. So what's another word we can use instead of emulsifier? Surfactant, good.
Which keeps the water molecules away from each other, allowing for smaller ice crystals to form. The second way to control ice crystal formation is by changing how fast the water freezes.
If you freeze your ice crystals very quickly, very rapidly, right, you get lots of little tiny crystals like this. If you let them freeze over a long period of time, you get bigger and bigger crystals at the end.
Proof that it's not just all sweet talk. That made ice cream 3 different ways. First, made ice cream the old-fashioned way, in an ice cream maker.
So what this does is there is a heat exchanger in the middle, so we get this really cold in the freezer, and this needs to freeze over the course of a day, maybe 2 days, to get all of the liquid inside of this container really cold. And what will happen is this will turn and churn our ice cream as it freezes. And this will take about a half an hour. So obviously this is a long time. And so our ice crystals out of this preparation are going to be a little bit bigger than some of our other preparations. Another way to cool down our ice cream base is to use salt and ice. And the salt changes the freezing point of the water, and so we can get lower temperatures with this bag of ice, right? With salt in it. Now we're going to play with liquid nitrogen. So what we want to do is pour slowly while we mix it up. So I'm mixing like I did in the dry ice for 2 reasons. One is whenever you make ice cream, you want to keep incorporating air into your ice cream. That it helps with the flavor and the stability of your ice cream. But also because we want to quickly transfer the liquid nitrogen through our liquid to cool it evenly.
Sugar and fats play a crazy important role in the flavor of ice cream. Cold tends to numb the taste buds, so consuming ice cream dulls the sensitivity of the tongue. This is why ice cream has so much sugar in it. Try tasting melted ice cream and cold ice cream. The melted ice cream will taste significantly sweeter. As far as the fat goes, unless the ice cream's label is light, low fat, or non-fat, ice cream must contain at least 10% fat from milk. Premium ice cream, the really good stuff, has up to 20% fat, which gives it a velvety, rich texture. So, we tasted the results, and that was right. The salt and ice cream was crunchiest. The ice cream maker ice cream was less crunchy, and the liquid nitrogen ice cream was incredibly creamy. Now, we're not...
So which was the crunchiest? Okay, salt and ice one. That's the version we're doing because we don't have liquid nitrogen. I am not liquid nitrogen certified. I'm working on it, and we don't have an ice cream maker here. So we're gonna do that one, and it's just ice crystals that are forming very, very rapidly, like over 15 minutes. And that's why it's crunchy, but it's still yummy. So I think you guys can handle that, right? Oops.
I'm not saying you have to buy liquid nitrogen and start blasting your ice cream with it, but at least you now know why your ice cream treat is so silky smooth. Hey, if you like learning cool things like this, make sure to hit that subscribe button. And while you're here, check out why bacon smells so delicious.
Bacon just-
still is made.
It's got a lot of good stuff in it. Yeah, you can watch that one later. Okay, so
the instructions are on the lab stations. They're provided on like in a plastic sleeve, so when you make a mess, it doesn't destroy my labs. Everything is on the back. Basically, I will be the milk pourer, so I don't have to cry over spilled milk. And I'm gonna give you a little extra milk because I think I have too much milk, and I don't want it to expire like next week. share the utensils because I only have so many tablespoons and teaspoons, and so we're gonna need that for every lab group. So just share. And if you're like, you know what, I'm not gonna share. I can figure this out myself. The plastic, little white plastic spoons I'm providing you is a teaspoon. So if you want to make a tablespoon, you just get 3 of those, right? So scoop, 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 and that's gonna be a tablespoon. It's not heaping scoops, though. It's kind of a leveled scoop. Whenever you get to the point where you're making the ice cream, your personal sandwich bag is yours. That's what you're putting milk, sugar, and vanilla in. That's yours. And there's going to be 2 of them because you're working in partners. Those go in a gallon bag, and in that gallon bag, what's going in? Ice and salt. Do not put the salt in your sandwich bags. Okay? Yeah, do not put the salt in the sandwich bags. Whenever you start to shake that, basically I'll just show you really an easy way to do it. I don't want you to freeze your fingertips off because they will get frostbite because this gets really cold. So I have a couple gloves, but I told you, I warned you, bring gloves. And you have some long sleeves. There we go, some long sleeve shirts you can use. Make sure, one person, everybody in second period was like, you were right. I was like, I know I'm right, I've done this before. If you get salty water someplace, then make sure you clean up because it leaves like a horrible mess. So we'll make sure that things are cleaned up before we get done, okay? As you're consuming your freezing point depression experiment, that's when you can begin answering some questions on the lab sheets. And there's, I'll tell you more back there, but go give them the partner set. Yeah. So some of our you need to go to a location that is there are 3 bags per lab station, and that means there's 6 people per lab station. We have so much food. Guys, you can count. You don't there's only 4 ladies right there. Read the procedure. I don't know what it's going to be. Read the procedure. Those are good with no safety lines. You can tell them how much I have ice on both sides of the lab. You guys can give me your station location. After this is ready, you can send me somebody's milk. Send me somebody's milk. One person's getting ice, the other person's getting milk.
Oh, it's so good. Six tablespoons of salt. -1. Ours is below Wait, this is Celsius. Here, I said about. That's pretty cool. Yeah, this is the center of the maybe we actually have so Alright, 6 tablespoons. Hey, Jacob. Hey, on the ice, you can sell your like little mixture of it. Okay, thank you.
See the thermometer, is it already? Oh, you guys, never mind. They are fragile, so don't like eat the thermometer with the ice. Maybe you're just seeing your initial That's a fire stone, right? Yes, that fire stone.
Yeah, I have.
And all of the instructions to the TV, I believe, we have plenty of salt. Here's some more salt. Like some more salt. Who needs salt? Who else needs salt? Who needs salt? Alright guys, here's how you're gonna shake when you're exercising. Alright, listen. 5, 4, 3, 2, 1. Okay, so this is the best way to do it. One person's gonna man up and hold the cold side, and they're gonna shake, 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 shake your knees. So you don't bust the back open, and then you're gonna shake this leg, and then you're gonna go like this. Oh, knees. Teamwork everywhere too. This big skill exercise is needed. Be careful with the thermometers in class. They will break. Be very careful with them. Alright, listen for me. 5, 4, keep listening. 3, 2, 1. Stop in for just a second. Okay, so 1, I already see that. It's not going to be like rock hard ice cream. It's going to be like a hard soft serve. So don't expect it's going to be like a rock, okay? So once it's like pretty firm and stuff, it is done. The ice, salt water will go in the sink. You'll dump it down the drain, and then you'll throw the gallon bags away. Okay? I don't want those nasty old gallon bags back. If it starts to leak, let me know and I'll give you another bag. Go.
Really? That's very cool. No, what is the other? He's definitely got a lot of
Well, it's not, it's gonna get some great light. It's not gonna, so, go ahead and see. I got that.
And so we get them for dismissal. Thank you.
Oh, poor baby. Poor baby. Yep, stuff, yep.